Um, I'll be talking about two algorithmic problems and their relationship in this talk. So this first problem you're all very familiar with. It's just the problem of optimizing a function over Euclidean space. And this problem, like we want to algorithmically find a point which is close in some sense to the minimizer of f. And of course, this is like an entire field and we have a lot of algorithms for this, but the most basic approach to the optimization in continuous time, you follow the gradient flow. You just keep traveling in the direction of steepest descent. And then in discrete time, we can discretize this by choosing some step size h and then following the gradient. Okay, so that's optimization. The second problem I want to talk about is sampling. And this problem is I'm given a probability density pi over Euclidean space, and I'm always going to write this density in the form x of minus v. So v is going to be called the potential function in analogy with thermodynamics. And in this algorithmic task, what we want to do is we want to generate a random point on our computer whose probability distribution is close to this distribution pi in some sense. Okay, so how do we solve this problem? The idea is like Markov chain Monte Carlo or MCMC. You like design some Markov process whose stationary distribution equals pi, and then you run this Markov process. So for this problem in particular, one very canonical way to do this is given by this diffusion. It's called the Langevin diffusion. It's a stochastic differential equation where you follow this like gradient of the potential, but you add some Brownian motion. And this too, like you can discretize this and you can implement this on a computer because the Brownian increments are just sampling from Gaussian distributions. And so before I talk more about the sampling problem, I want to make this problem like very concrete for you. Like why do we want to solve this problem? Where does it come up in practice? So let me just give you like this textbook 101 example of like why like sampling helps us to do statistics. So here's a very basic stats problem. Let's say that you have a bunch of people and associated with the ith person, you have some like vector of covariates that you've, a bunch of like features about this person that you've collected, maybe like their browsing history or whatever. And based on like all this information you have about this person, you want to predict some attribute about this person. For instance, like whether this person likes jazz, whether this person will buy your product, whatever. Okay, so how do we like set up a statistics problem like this? Well, like you can start by just formulating some statistical model for this problem, which is like, let's suppose that the probability of yi being 1 given this vector of covariates is given by some function of your covariates, which depends on this unknown parameter theta. And the job of statisticians is to infer what this parameter theta is. Now, if you in particular want to adopt a Bayesian approach to this problem, then what you do is you specify some like prior belief, some distribution over the possible thetas. And then Bayes' rule will tell you how to update your prior belief to give you a posterior distribution. And then if you like work out what Bayes' rule tells you for this problem, you get the posteriors of the form e to the minus v, where v is this function. All right. So now like what do we want to do with in Bayesian inference? Like one basic thing you want to do is just compute the posterior mean of this distribution, which is just the average under this distribution. And v was that expression that I showed on the previous slide. So as you can see, like, well, we've gotten this far, but then like just by looking at this expression, it's not immediately obvious how you can quickly solve this problem on your computer. In particular, like this involves like computing some very high dimensional integrals, and our goal is to not like discretize all of space into like tiny grids, because we know these grids are going to have to scale exponentially in the dimension. So the basic idea behind MCMC is as long as we could just draw random samples from this posterior distribution, then as long as we can average these samples, then we'll get a good approximation for the posterior mean. So that's what we want to do. And this will maybe give you a little flavor of the computational problem. As you can see, like in many situations, this function v is like fairly explicit. So you can evaluate it, you can like compute its derivatives and so on, but it's still like this, the integrals are hard to compute directly. So this is what I said, like we're going to assume you can maybe evaluate v and its derivatives. And of course, like Bayesian inference is like an important problem. It's used like in many applied sciences, but I would argue like nowadays, like, I mean, just think about how many times you've heard the words like data science in the past year. Like probabilistic reasoning is becoming like really prevalent in today's world, and like as it continues to be important, like I would argue the sampling problem is a pretty basic fundamental algorithm task, and we just want to know how to solve it in lots of other applications. Right, so now comes the punchline, which is the connection between these two problems I started off with, optimization and sampling. So this is this wonderful result due to Jordan, Kinderler, and Otto. And it says the following. So remember this Langevin diffusion that I told you about. Let's consider the marginal law of this distribution at time t, mu t. So this is a probability measure. Now, it turns out that if you take the space of all probability measures and you equip it with a certain geometric structure, then it's almost like a Riemannian manifold. This geometric structure comes from the theory of optimal transport due to like Monge, Kantorovich, and others. It's also like gives rise to what's called the Wasserstein distance. And if you take this geometry over the space of probability measures and you follow the gradient flow of a certain functional on this space, and this functional is the relative entropy with respect to the distribution pi, then this gradient flow is exactly describing the evolution of the marginal distribution of the Langevin diffusion. So what this tells us is like a very geometric picture of what this Langevin diffusion is doing on the space of distributions. It's like following the steepest descent of this very interpretable objective function. And moreover, this gives us the link between optimization and sampling, namely like this MCMC algorithm, you can actually view as an instance of optimization, it's following the gradient flow. And so like based on starting from this result, you can start to see like how much can we translate from the field of optimization to this problem of sampling. So we saw that the gradient flow translates into this diffusion. In convex optimization, like we make the important structural assumption of convexity of your objective function, and we know that this is a very, very nice assumption that allows our optimization problem to be tractable. The same way, like the corresponding assumption in sampling is convexity of this potential function v. But because pi is e to the minus v, then this is also called log-concavity of pi. And log-concavity also has a lot of like interesting relationships with convex geometry, high dimensional probability, and so on. So these that kind of enter into the study of sampling. And more generally, like this kind of perspective, like although MCMC and Markov processes have been studied for a long time, it's like this kind of link with optimization that ushers in kind of the modern theory of sampling. So let me give you like another example of how we can hope to translate concepts from optimization to sampling. So this is like perhaps like the crown jewel of the theory of optimization. One of the surprising results in this field is that this gradient descent algorithm is actually suboptimal, at least for instance, like smooth convex optimization. But let me like explain to you a little bit what it means. And I think it is surprising because like gradient descent is, you know, an extremely natural algorithm. And yet we're saying like there's a better way to somehow like combine local information about your function to minimize it. So this is like the non-asymptotic guarantee you can prove for gradient descent that the error you make decays like 1 over the number of iterations. But of course, like in algorithms, you always ask that, can we do better? And asking like whether you can do better actually requires a little bit of thought because like implicit in this question is like a lower bound, like what are the limits of what we can achieve?
Could you tell us what the bad case is that we're fighting against?
I'll explain like in a little bit, I guess. Okay, I'll come back to it. Right, so to say like why this is a little bit subtle, it's because like we have very poor lower bounds for computational complexity in general. And what we're after here is a really refined result, like very specific dependence, not just like polynomial time versus non-polynomial time. So the way that you start to formulate this question in a way that's amenable is via the idea of an oracle model. So this oracle model is like, okay, suppose that actually f is completely unknown to us. We can only access it by asking an oracle in the following way. We like give the oracle some point x, And then this oracle spits back for us like the value of the function and its derivatives at x. Okay, so now the problem of optimization is kind of a game. Like I keep querying this oracle and then I want to know like what's the minimum number of times I need to do so. And because we've translated to an information theoretic problem, now you can actually prove some lower bounds for this. And in this oracle model, Nemrowski and Uden showed that the lower bound for smooth convex functions is 1/n squared, which is like smaller than the upper bound for gradient descent that we saw. And indeed, like motivated by this result, Nesterov showed an accelerated method for optimization that actually achieves this lower bound. Now to go back to your points. Okay, so you could look up like exactly what is the function that they used in this lower bound instance. I don't remember it off the top of my head, but essentially like the structure of the function is such that if you only follow the local information, you kind of only explore like one dimension at a time. And then you can like work through the calculations and show this lower bound. Okay, so what does this accelerated method for optimization kind of look like? Well, here's like a simplification of it in continuous time. It kind of looks like this system where we've added this new variable p, which is like a momentum. The position is evolving by the momentum. The momentum has this gradient term and a friction term. And this system, you can try to translate into sampling by making a stochastic differential equation where you add some noise. So this is like in sampling what we believe to be the analog of acceleration. Now, like this process on the right actually turns out to be a pretty like fundamental process in its own right. So one way you can tell that it's fundamental is if it comes from physics, and indeed like the study of this process goes back to Kolmogorov. This is kind of like the canonical model for like gas particles, which are like in collision and under like friction and a confining potential. And like this like physics model, like now we're using almost a century later for algorithmic purposes, which is kind of cool. So also like it's pretty interesting mathematically. Notice that the Brownian motion is only added to one of the coordinates. So this is actually a degenerate diffusion. So in the language of PDE theory, this equation is what's called a non-elliptic but hypoelliptic equation. And indeed, like this process was a powerful motivation for Lars Hormander to like establish his theory of hypoelliptic second order differential equations. So that was like in the 60s, I guess, but in order to use this for algorithmic purposes, we need not only regularity, but convergence estimates, like how fast this process will converge. And this was like kind of developed in this monograph by Villani. But these results, like they're very general, but not the sharpest possible conjecturally. So even today, like this question I started off with, like whether there's an analog of acceleration in sampling, still remains open because we still don't have like sharp enough estimates for this. And so this is kind of emblematic of this kind of area as a whole, where like we take ideas which have been like utilized in optimization for 40 years and we try to translate them into the realm of sampling. And indeed, like a lot of the work that I did over the past few years is trying to achieve just that. But just as we saw, like even when you take pretty like well understood concepts in optimization, once you move to the land of sampling, suddenly the ideas start to get like a lot more rich. Now they start to involve some interplay between geometry, probability, PD, and other kinds of mathematical ideas. And as a result, there's still lots of questions in this field that we don't know the answer to. And that's it. Thanks for
questions. Why is that called accelerated? It seemed you had a friction term.
Are you asking like why it's called acceleration or why it's actually faster?
Why it's actually faster.
Why it's actually faster? Well, you can.
Is it sort of correcting some tendency to overshoot that would have otherwise happened?
Yeah, you can think like the momentum is keeping track a little bit more of the history, so that you don't like have this like undesirable bouncing behavior. Instead, you'll kind of head towards the minimizer faster.
questions. Okay, thanks again.